In this video, we present a simple result about the properties of polynomials over a field. This property has to do with the multiplication and addition of polynomials. We define the degree of a polynomial over a field. We understand how the degree relates to the multiplication and the addition. We give a proof of this result, and we also outline a convenient method for multiplying polynomials using the box method. We begin with some simple definitions. So let f be a polynomial over the field capital F. For a fixed n depending on f, write f as the sum, as j goes from 0 to n, of the product of the coefficients of f, that is fj, times the powers of x in increasing order, that is x to the power j. We say that f is monic if its leading term, that is the coefficient on the highest power of x, is equal to 1. And we say that it is scalar if all its coefficients except for its constant term are 0. We call the degree of f to be the value of the exponent on the highest power of x. The set of polynomials over the field f is written as f bracket x. X is the variable unknown that we use in our polynomials. Now, f infinity is the collection of infinite strings of scalars from f in order. It can be shown that f infinity equipped with addition and scalar multiplication, addition in the usual sense of component-wise addition, and scalar multiplication in the usual sense of component-wise scalar multiplication, turns f infinity into a vector space. Moreover, one can consider f of x to be a subspace of f infinity by embedding it into it in the following way. For a polynomial f, write it as the infinite string gk as k ranges over the non-negative integers. Here, gk is allowed to be the kth coefficient of f, that is fk, for k less than or equal to n, and for k greater than n, you write gk as 0. Using this notation, one can write that x to the power k equals delta sub kn, where delta is the Kronecker delta. Here n ranges over the non-negative integers. So, for k different from n different from k, we have that delta kn equals 0, and for n equal to k, we have the delta kk equals 1. Some examples of this are given now. We write the examples for x, x squared, x cubed, x to the 4. For x, you simply write 0, 1, 0, 0, 0, 0, 0, and an infinite string of zeros. X squared is 0, 0, 1, 0, 0, 0, 0, that is an infinite string of zeros after the 1. X cubed is a string of 3 zeros followed by 1 and then an infinite string of zeros. X to the 4 in similar fashion is a string of 4 zeros followed by 1 and then an infinite string of zeros. In this way, we are able to write every single power of x as an element of f infinity. Those are infinite tuples of scalars in a given order. Here we come to our main result. Let f of x be the subspace of f infinity spanned by the vectors 1x, x squared, x cubed, and so on. That is all the powers of x, all the non-negative powers of x. An element of f of x is called a polynomial over f. Now, let f and g be non-zero polynomials over f. Then, we have 5 different consequences. First, fg is also a non-zero polynomial. Second, the degree of fg equals the degree of f plus the degree of g. Third, fg is a monic polynomial if both f and g are monic polynomials. Fourth, fg is a scalar polynomial if and only if both f and g are scalar polynomials. And fifth, if f plus g is non-zero, then the degree of f plus g is bounded above by the maximum of the degrees of f and the degree of g. Before we proceed to the proof of that result, we start by outlining a method for multiplication of polynomials using a table. The table here helps to visualize the multiplication as it happens in f of x. We illustrate some properties of this multiplication. We take the example of f equal to 1 plus 2x plus 3x squared and g equal to 3 minus 4x plus 7x cubed. We write out f and g as elements of f infinity as infinite tuples from the scalar field f as described before. So f contains a finite number of non-negative, non-zero scalars, the coefficients being 1, 2, and 3 in order, and then an infinite string of zeros. Similarly, g contains a finite list of non-zero scalars followed by an infinite list of zeros. To start with the finite component, that is 3, negative 4, 0, and 7. And then after that what follows is an infinite string of zeros. That is what we have written here. In the first row, here at the bottom, we've written the scalar component description of f, and in this first column in green, here we've written the scalar component description of g. Now, the second step now is to multiply cell by cell the numbers that appear at the intersection of rows and columns. This corresponds to the multiplication of coefficients of f and g. We take first the constant term of f, that is 1, and multiply it by all of the coefficients of g. Those are 3, negative 4, 0, and 7. So these numbers multiplied by 1 leave them unchanged, giving us 3, negative 4, 0, and 7 again. Multiplying these coefficients of g by the scalar 2, which is the coefficient on the linear term of f, which is 2x, gives us 3 times 2 is 6, negative 4 times 2 is negative 8, 0 maps to 0, and 7 times 2 maps to 14. Lastly, the coefficient on the quadratic term is 3 for 3x squared, and we multiply 3 by each of the coefficients of g. 3 times 3 giving 9, 3 times negative 4 giving negative 12, 0 maps to 0, and 3 times 7 gives 21. Now, we need to add up these products across diagonals to be able to add like terms of like powers of x. This is done using the following description. The purple lines indicate the numbers that need to be added across diagonals. The reason for the addition across diagonals here is because this is the only way one can obtain like terms in this product representation over the table. So for the linear terms, for the constant terms, one has only 1 times 3. That gives 3. For the linear terms, one gets 2x times 3 as 6 and negative 4x times 1 as negative 4. Adding these two gives 2. So we've written down in this table these sums. So the constant term is 3, the linear term is 2 as coefficient 2. Now for the quadratic term, we have 9 plus negative 8 plus 0. So 9 comes as 3x squared times 3. Negative 8 comes as 2x times negative 4x, which is negative 8x squared. And there is no contribution to any other quadratic term. with the multiplication of 1 with any coefficient of g. That's why we get the 0. So 9 minus 8 is 1. So the coefficient on the quadratic term is 1. Now for the cubic term, we get negative 12 from 3x squared times negative 4x as negative 12x cubed, and we get 7x cubed coming from 7x cubed times 1. There's no contribution from 2x with any term of g to give a cubic term. Negative 12 plus 7 gives negative 5, so that's the coefficient on the x cubed term. Now for the quartic term, we have simply 14 that comes from 2x multiplied by 7x cubed, and that's the only way to generate a quartic term here. 3x squared does not multiply with anything over here in g to give a quartic term, and neither does 1. So the quartic term has coefficient 14. And lastly, the quintic term has coefficient 21. That simply comes from 3x squared times 7x cubed. So it follows that the product f times g is given as 3 plus 2x plus x squared minus 5x cubed plus 14x to the 4 plus 21x to the power 5 by summing along diagonals. Now, we attempt another example, this time with f equal to 3x minus 7 and g equal to 1 plus 2x plus 9x cubed. We again write f and g as elements of f infinity. So f can be written as negative 7, 3 with an infinite tail of zeros. G can be written as 1, 2, 0 for the quadratic term and 9 for the cubic term, and then an infinite string of zeros, which we do not care about. Again, we multiply cell by cell of the numbers at the intersections of rows and columns. Taking the constant term of f, that is negative 7, and multiplying by each of the coefficients of g, those are 1, 2, 0, 9 in order, we get negative 7 as 1 times negative 7, 2 times negative 7 gives negative 14, 0 maps to 0, 9 times negative 7 is negative 63. And now, for the coefficient on the linear term of f, that is 3, multiplying it by 1, 2, 0, 9 gives 3, 6, 0, and 27. Again, we need to sum across diagonals in the following way, and here we show the results. The constant term stays as negative 7. The linear terms are negative 14 and 3. This comes from negative 7 times 2x and 3x times 1. That gives negative 11x. Quadratic term is simply 6x squared coming from 3x times 2x. The cubic term is simply negative 63 x cubed coming from negative 7 times 9x cubed, and the quartic term comes as 27. That's by the multiplication of 3x with 9x cubed. So summing along diagonals, we get f times g is equal to negative 7 minus 11x plus 6x squared minus 63x cubed plus 27x4. Now we come on to the proof of the result that we've stated before. We need to prove that fg is a non-zero polynomial, and we need to prove a lot of other results about the degree. So suppose the degree of f equals m and the degree of g equals n, and let k be a non-negative integer. Now, from the method or the formula for the product of polynomials, we know that the coefficient in fg of x to the power m plus n plus k is given as the sum of fs times gt with the condition that s plus t sums to this power on x, which is m plus n plus k. This is standard. Now, in order that we get non-zero terms fs and gt, so that the product is non-zero fs times gt, what we need is that s is not exceeding m and t does not exceed n. This now implies that the sum s plus t is at most m plus n. And when we combine that with the condition that s plus t equals m plus n plus k, what we're left with is that k has to be 0. There is no other choice. So we have that coefficients on x to the power r are 0 for r greater than m plus n. On the other hand, the coefficient on x to the power m plus n in fg is given as fm times gn, which is non-zero. So it follows that the degree of fg equals m plus n. This is because the coefficients on all powers of x greater than m plus n has been shown to be 0 already above, and the coefficient on x to the power m plus n is shown to be non-zero, as both fm and gn are non-zero by assumption or by definition. In other words, writing this as a formula, we have that the coefficient in fg of x to the power m plus n is simply fm times gn. If fm and gn are non-zero, that means that fmgn is non-zero, and that means that at least one of the powers of x, namely x to the power m plus n, has a non-zero coefficient, and so fg is non-zero. Further, we can write that degree of fg equals the sum of the degrees of f and g, as already established. Now, if f and g are both monic, meaning that their leading terms fm and gn are 1, then the leading coefficients are 1, then the coefficient on x to the power m plus n, the leading coefficient on fg, is also 1, because that is the product of 1 times 1, which equals 1. So we conclude that fg is monic when both f and g are. In addition, when m equals 0 and n equals 0, we have the degree fg equals 0, and fg is scalar when both f and g are. This is because the degree of f and g was shown to be the sum of the degrees of f and g. Conversely, if fg is scalar, meaning that the sum of the degrees of f and g is 0, then that forces both the degrees of f and the degree of g to be 0, meaning m equals 0 and n equals 0, and both of them are scalar. So we've proven the equivalence that fg being scalar is equivalent to both f and g being scalar simultaneously. Lastly, we need to come up with a bound on the degree of the sum of two polynomials. So notice that when we add up the polynomials f plus g, we incorporate the sum fm times x to the power m plus gn times x to the power n. These are simply the sums of the leading terms of both f and g. Without loss of generality, it can be assumed that m is at least as big as n. Then surely the degree of f plus g cannot exceed m for x to the power m is now the largest power of x with a non-zero coefficient. It might well be 0, and there may be conditions for that. But there cannot be a power of x bigger than m which is non-zero. For if that were the case, then that term would have to be incorporated either into f or into g, or both. So with this first bound out of the way, now there could very well be a case where the degree of f plus g is much less than m, or not equal to m. So for this, we would need that the leading terms of f and g, that is fm x to the power m plus gn x to the power n, cancels out, meaning that it vanishes. This is only possible if m equals n and the coefficients fm and gn sum to 0. In that case, the degree of f plus g is strictly less than m equal to n. But if either one of these conditions fail, so if m is greater than n, meaning m is not equal to n, or if the sum of fm and gn is non-zero, then the degree of f plus g is equal to m, because then the coefficient on x to the power m is definitely non-zero, which is fm, and that has to be non-zero by definition. So we finally have the upper bound that the sum of the degrees, the degree of the sum of f plus g is bounded above by the maximum of the degrees of f and g. With this, we conclude our proof and the video, and I thank you for watching, and I hope to see you in the next video for a continuation of these ideas on polynomials over fields.